Today we are going to discuss some behavior of functions. That means how does a function behave when the variable based on which the function is defined, the variable under consideration goes to a particular value. So this in turn implies that what is the value of a function, say let's say f(x) when x tends to some particular value, some maybe finite value. So this we call the limit of a function, and associated with the concept of limit of a function, that means what is the behavior of the function when x or the variable under consideration goes somewhere to a particular value. Associated with this concept, the very important concept is there that will come automatically, which is known as continuity. That means we have to define what is the meaning of continuity, in other words, when a function is said to be a continuous function. So in this talk, we will keep it very, very simple. Instead of discussing too many theorems or results, we will focus on defining the limit of a function and when a function is continuous, or rather the continuity of a function at a particular point. And we explain this concept because it is very important to understand the concept of limits and continuity. So in order to understand this thing clearly, we have demonstrated this concept or this two important notions using a couple of examples under various cases. That means when a function might have a limit, or when a function might not have a limit, or when a function is continuous or it is discontinuous, like that. So we have also discussed a couple of examples which will elucidate these several facts about limit and continuity relating to a function. So first we will set the objectives. This talk is first we will define what is the meaning of limit of a function, and then we discuss few theorems. I might not elaborate the proofs of the theorems because that is very easy. Just give an outline of that. Then I will define continuity and the definition, and I will explain it in various cases using some examples. So first, a limit of a function. What is the meaning of it? The definition goes by this. Suppose we have a function of a real variable, of a single variable, say x. That is, the function is f(x), and it is defined in some open interval E containing a point A. Now remember, we are not going to insist that f should be defined at that particular point A itself. Assume that L be a real number. We write f(x) goes to L as x goes to A, which means that for every epsilon positive greater than 0, epsilon might be arbitrarily small, there always exists a delta which is again small but positive, delta greater than 0, such that modulus of f(x) minus L is less than epsilon whenever modulus of x minus a less than delta. What does this mean physically? This means that if we consider an x which is in a very small neighborhood, that is a delta neighborhood of a, that means which is within a very small distance from a on either side, this will always imply that f(x), the distance between f(x) and another real number L, will always be less than some arbitrary positive quantity. That means they are very close to each other. So in that case we say that the limit of a function exists, and limit of f(x) is nothing but L as x is very close to a or x goes to a. The notation we use is that lim x goes to a f(x) equals to L. So this is the formal definition of limit of a function of a real variable. Now let us consider a few facts as remarks, that instead of defining on a subset of the real line, we can always define limit of a function on general metric spaces, of course with appropriate metric. Now here metric is nothing but kind of distance measure on those metric spaces in which we are interested, and based on or using this appropriate metrics, we can always define a limit of a function which is defined on these metric spaces. Secondly, f may not necessarily be defined at the point A itself. We have already explained this, we have already mentioned this. Even if f is defined at x equals to a, we may very well have that the limit exists, that is limit f(x) x goes to a exists, but that is not equals to f a. We will explain this thing using an example. So basically this gives some idea about the meaning of the limit of a function of a real variable, and it is important to note that although we are defining the domain of x as a subset of the real line, we can always think of this entire setup on a general metric space. but remember we have to define the appropriate metric under which we can define the limit of the function on that particular metric space. And one important thing is that if x has a limit x equals to a, that means at the point x equals to a, if a limit of exists, then this limit is unique. We cannot find two different limits that exist at a particular point. The proof is extremely simple. I am just going to omit that proof. One small theorem, but very important, which is very obvious, but it is important to write it formally. Suppose E is a subset of R, that is, E is a subset of the entire real line, and A is a limit point of E. Now remember, since A is a limit point of E, it may not belong to E itself. F and G are defined on E. Then limit as x goes to a, limit of sum of two functions f(x) and g(x), which are already defined on E but may not be defined on a, equals to sum of the limits, that is limit x goes to a f(x) plus limit x goes to a g(x). Similarly, if we consider the product of these two functions, that is f(x) into g(x), and take their limit as x goes to a, this will exactly equal to the product of the respective limits. That means limit x goes to a f(x) into limit x goes to a g(x). Now one can always think of what happens if we consider the quotient, that is f(x) by g(x). So again, limit of this ratio of two functions, that is limit of f(x) by g(x) as x goes to a, this is nothing but the ratio of the two limits, that is limit of f(x) x goes to a divided by limit of g(x) x goes to a, provided of course the denominator must not be equals to 0, that is limit of g(x) x goes to a is not equal to 0. So in the same line we can think of several other theorems, but again the proofs are very simple, because just apply the definition of the limit or the definition of or the condition of existence of limit, and there is a modulus sign, so manipulate with that modulus of the difference, immediately get the result. So few facts. Usually while studying limits, we usually come across two terms. One is known as left hand limit, another is known as right hand limit. So we define right hand limit as a limit x goes to a plus f(x). That means as x approaches to a from the right side of a or from the higher values of a, and suppose this limit is equals to L1, then L1 is known as the right hand limit of f(x) when x goes to a plus. Similarly, when x approaches to a from the left side of a, that is from the lower value of a, and if we consider limit of f(x) as x goes to x is coming to a from the lower side or from the left side, and if this value is L2, if it exists, then we say L2 is the left hand limit of f(x) as x goes to a. And now the existence of limit can be defined in terms of this left hand limit and right hand limit. It is pretty obvious. If we look at the definition of existence of limit, it is pretty obvious that if L1 equals to L2, we can immediately say that the limit exists. Now remember one thing, L1 equals to L2 equals to L, say, that means the limit exists and the value is L, then that does not necessarily imply that this L is equal to fa. So if f is defined at a, we will get some value of f at the point a, and remember a might not belong to strictly E, but maybe a limit point of E. On the other hand, if the limit exists, that means left hand limit and right hand limit are equal and equal to say L, then L may not be equal to fa. L may be equal to fa, but in many cases L may not be equal to fa, although we say that the limit exists. Now this idea gives us another concept that, so there are two situations. Consider the situation when the limit exists, and under this there are two situations, that when left hand limit and right hand limit are equal, but this equal value, this value is not equal to the value of the function at that point, that is value of function f at a, and another situation when L is equal to fa. So this immediately gives rise to another concept which we are going to discuss within a few minutes. Few examples. I consider a very nice function like parabolic function f(x) equals to x squared plus 3 when x belongs to R. That means this is defined for both positive and negative values of x. In fact, positive and negative real numbers, real values of x. Now we want to check whether the limit exists at x equals to 0. So now limit f(x), consider the right hand limit, that means x is approaching to 0 from the positive side of 0. That means x is taking positive values and continuously approaching to 0, but not equals to 0 in this case, and that limit is equals to 3. And when we consider the left hand limit, that means x is approaching towards 0 from the negative values or on the left hand side left values of 0, then limit of f(x), x goes to 0 minus which we denote this as equals to 3. In this case, in fact, f0 is exactly equals to 3. So first two conditions, that means right hand limit and left hand limits are equal. That means that will imply that the limit exists. And in this particular example, we see that this limit of this function, which is indeed 3 when x goes to 0, is equal to the value of the function at x equals to 0. So the question is, can we have an example where the limit exists but the functional value at that point is not equal to the limit? We will come to that, but before that, this is the graph of this function. It is clear that the function is really smooth, and the blue line means the function is coming from the x is coming from the right side, and the function is approaching to a value which is 3, denoted by the red dot, and black curve gives us the movement of the functional value as x goes from the negative side of 0 towards 0, and if 0, that means the red dot gives the value of the function at x equals to 0, which is indeed 3. Let us consider another function, that the same kind of function f(x) equals to x squared plus 3 when x not equals to 0, and we change the value of f(x) at x equals to 0, let us say it is 4. Then it is clear that limit exists at x equals to 0. In fact, because limit f(x), that means right hand limit of f(x) at 0 equals to 3, which is equal to the left hand limit of f(x) at 0, which is indeed 3, that means limit exists. However, it is clear that is not equals to 3. So the graph looks like this. You see that the blue part is very smooth. The function is coming down as x is coming towards, x approaches towards 0 from the right side or from the positive sides of 0, and another smooth curve is denoted by the black color from the left side. It is again coming down to the value of 3 when x is coming through the negative values of towards 0, but they are coming exactly at the same value, that is at 3, but when it reaches 0, that means when x equals to 0, the value is not equals to 3. There is certain kind of gap at x equals to 0. So we will study this kind of gap in a few minutes. Another function is, say, f(x) equals to x squared plus 3 when x greater than 0, and x squared plus 4 when x is less than 0. Now here, if we consider right hand limit, then we see that f(x) equals to 3, that is limiting value of f(x) equals to 3 as x goes to 0 plus, and f(x) equals to 4 as x goes to 0 minus. So clearly, as x approaches to 0 from one side, we are getting one particular value, but when x approaches to 0 from the other side, we are getting a different value. So right hand limit and left hand limit are not equal, and hence we say that the limit does not exist at x equals to 0. The curve looks like this. It is clear that there is sudden jump at x equals to 0, and they are not actually approaching from either side to the same value. So we cannot say that the limit exists. In fact, the limit does not exist in this case at x equals to 0, but for other values of x, limit exists. That is very clear from the graph and also from the nature of the equation. Let us now discuss that particular gap which we call a discontinuity, or rather we will study continuity of a function. The formal definition goes like this. Like previously, here also we consider f to be defined in some open interval E containing a point A, and f is also defined at A. This is very important. F is also defined at A. Then f(x) is called, or f is said to be continuous at x equals to A as x goes to A if for every epsilon greater than 0 there exists a delta greater than 0 such that modulus of f(x) minus f(a) less than epsilon whenever x minus a less than delta. So when you want to check the continuity of a function at a particular point, in this case at a particular point x equals to a, so we will approach a from either side of a. That means x goes to a plus or x goes to a minus. So naturally this indicates that it has something to do with the left hand limit or right hand limit at the point a. And if we see that as x approaches to a, or as x is very very close to a, or the distance between x and a is very very small, then if f(x) and f(a) are very close to each other, or rather the distance between f(x) and f(a) as indicated in this case is modulus of f(x) minus f(a) is extremely small, then we say that f(x) is continuous at x equals to a. In other words, f(x) is said to be continuous if clear that if right hand limit of f(x) is equals to left hand limit of f(x), which is indeed equals to f of a. f(x) is defined at that point a. So now it is clear that this is very important, that the question we have to check whether fx is defined at that particular point where we are trying to investigate the limit of the function or the continuity of the function. And depending on the fact that f a is equal to left hand limit and right hand limit, we can determine the continuity of that function at that particular point. Let's consider a few remarks that instead of again considering or defining on a subset of real line, we can also define continuity on general metric spaces, but we have to define appropriate metric when we deal with any general metric space. And with respect to that particular metric, we can only define the continuity of the function. And naturally, we can have a theorem similar to theorem 1, that is sum, product, etc. This kind of continuous functions are also continuous. So now since we have defined that whether a function is continuous or not, we have seen that the function may not be continuous. That means that point where a function is not continuous is known as point of discontinuity. Now we are going to find kind of discontinuity or try to investigate the nature of this discontinuity, and we are trying to define it properly. So let's f is defined, let it be defined on an open interval AB, which is a subset of real line, and if fx is discontinuous at a, that means we are assuming that f is discontinuous at a, and if right hand limit and left hand limit both exist, that means f of a plus and f of a minus both exist, then f is said to have a discontinuity of the first kind or a simple discontinuity. As for example, there are two situations. One is f of a plus is not equals to f of a minus, that means left hand limit is not equals to right hand limit, that is also simple discontinuity. Another thing is that this f of a plus and f of a minus might be equal, but they are not equal to f the functional value at that point, that is f a. So f of a plus equals to f of a minus, which is not equals to f a. Both are treated as simple discontinuity or for discontinuity of the first kind. That means here left hand limit and right hand limits both exist. So naturally, discontinuity of the second kind means if either one of this left hand limit or right hand limit does not exist. As an example, if we consider fx equals to mod x, where x belongs to real line, if we just look at the curve, it is clear that the function seems to be continuous, and there is a question that at x equals to 0, there is a slight notch, there is a slight sharp edge. So let us investigate whether the function is continuous at that point, because otherwise the function is continuous, which is pretty obvious. So the first we check whether the limit exists at x equals to 0, and it is clear that from the definition of mod x that limit x goes to 0 plus f of x equals to 0, that is right hand limit of fx at x equals to 0 is 0, and left hand limit of fx at x equals to 0 is also 0. Now what is the value of this function at x equals to 0? It is in fact 0. So f0 is 0. So it is clear that right hand limit at x equals to 0, right hand limit equals to left hand limit equals to the value at that point, functional value at that point. So the function is continuous at x equals to 0, and the function is continuous elsewhere. That is pretty obvious, since we can immediately say that the function is continuous everywhere. But note that it can be shown immediately that fx is not differentiable at x equals to 0, but otherwise it is differentiable. It is not differentiable only at the point x equals to 0. Now consider the second function, which is very interesting. It's very difficult to draw this function. Fx equals to 1 if x is rational, and 0 if x is irrational. So it is clear that f has a discontinuity of the second kind. That means that neither f of x plus nor f of x minus exists for every x. That is very important. So the idea is very easy. That means if we consider any value x equals to say 2, then we can think of a sequence of numbers which are sequence of rational numbers approaching to 2 from the right side. That means the limiting value would be 1. We can always find another subsequence which is a subsequence of irrational numbers, again approaching to x from the right side, giving right hand limit to be equal to 0. That means it is clear that right hand limit does not exist. Similarly, we can show that left hand limit of fx at every x does not exist. So hence this is a discontinuity, but of the second kind. Again, we just change this function little bit. Fx equals to x if x is rational, and 0 if x is irrational. Again, by the same logic, it is easy to see that f is continuous at x equals to 0, but has a discontinuity of the second kind at every other point. So only at x equals to 0 we can show that this is continuous, exactly following the similar argument as just discussed. and otherwise at every other point it has discontinuity of the second kind. That means neither right hand limit nor left hand limit exist at the point other than x equals to 0. At the end we propose another function, not really complicated but piecewise function, if x equals to x plus 2 when 0 less than equals to x less than 2, but when x equals to 2 f(x) is 3. When x is greater than 2 and less than equal to 4, then the function is 6 minus x. When 4 less than x less than 6, function is x, and if x greater than equals to this, the function is 0. Without doing any calculation, first let us look at the graph of this function. The graph looks like this. It is immediately clear from our discussion about limit and continuity of a function, it is immediately clear that interesting things only happen at x equals to 2, 4 and 6. And we see that at x equals to 2, left hand limit and right hand limit both exist, but it is not continuous, because at x equals to 2 the value is 3, whereas the right hand limit and left hand limit value, that means both sides, from the both sides of 2 the functional value converges to the value of 4, but this is not the value at x equals to 2. So, there is a discontinuity at x equals to 2. There is a discontinuity at x equals to 4, because from the left, when the function approaches, or when the value of x approaches from the left side of 4 towards 4, the functional value approaches to 2, but when x approaches to 4 from the right hand side, the functional value approaches to 4. That means there is a clear discontinuity at x equals to 4. So, at x equals to 6, the function is not really smooth, but if we check, the function is continuous at 6, because from the left side, as x approaches to 6 from the left side, the functional value approaches to 6, and from the right side the functional value approaches to 6 again. So, the function is continuous at 6. So, with all these things, it is clear that the function is continuous, but we need to investigate what happens when at x equals to 2, 4 and 6. As we have just described, at x equals to 2 and 4, the function is discontinuous, or has discontinuities of the first kind, that means limit exists. But important thing is that discontinuity of this function at x equals to 2 can be removed defining f2 equals to 4. That means just changing the functional value at x equals to 2, then the function will be continuous at x equals to 2. But discontinuity at x equals to 4, that cannot be removed by just changing the value of f at that point of discontinuity. So, this kind of discontinuity is called non-removable discontinuity, whereas discontinuity of the first kind at x equals to 2 is nothing but a removable discontinuity. And it is clear that the function is discontinued at x equals to 6, but it is not differentiable. That part is pretty clear. So, this gives us some idea about the nature of the discontinuity of a function, and sometimes just by changing little bit of definition of the function without much effort, we can remove a few discontinuities, but not all discontinuities. So, today we have defined what is the meaning of limit of a function, and when a function can be said to be continuous at a particular point. We have also illustrated these two concepts using various examples under various scenarios, as for example, a limit might exist, a limit might not exist. A limit might exist, a function may be continuous, a function may not be continuous. At the same time, a function may be continuous at some portion and it is discontinuous at other portion. We have also discussed a few examples where it is seen that it is easy to remove the discontinuity that is present in the function just by changing the definition of a function a little bit, and sometimes we have seen that it cannot be done. The function is defined such that one cannot remove the discontinuity. So, various properties of a function we have discussed, which is extremely important in order to understand the behavior of a function, and based on this one can go on to deduce various theorems and various results related to a function or the behavior of a function of a real variable. And one can obviously extend this entire concept when there is more than one variable. That means when a function based on more than one real variables. But today we have discussed only the concept and illustrated this with the help of a couple of examples.